This is a continuation of section 3.3 notes where we're exploring measures of variation. There's something called the range rule of thumb, which states that for the vast majority of data sets, 95% of our values lie within 2 standard deviations of the mean. Therefore, if we wanted to estimate a standard deviation and we know the maximum and the minimum, or in other words, the range of the data set, we would take that and we divide it by 4. 2 standard deviations on the high side, 2 standard deviations on the low side is where that 4 standard deviations come from, and that's going to give us an estimate of the standard deviation of the data set. The other way we can apply the range rule of thumb is if we know the mean and the standard deviation of a data set, we can find the minimum and maximum usual values. Remember, 95% of our data falls within 2 standard deviations of the mean, meaning it's between 2 below the mean and 2 standard deviations above the mean. So the minimum usual value is just the mean minus 2 times the standard deviation, and the maximum usual value is the mean plus 2 times the standard deviation. As an example, let's estimate the standard deviation for these Best Actress winners. If we scan this table, we see that the minimum age is 21 and the maximum age is 80. In most cases, this data is going to be in order and it's going to be easier to find those. So that gives us a range of 80 minus 21, or 59, and the range rule of thumb says we divide that by 4. Okay, that gives us an estimated standard deviation of 14.75. Applying the other part of the range rule of thumb, let's say we're looking at pulse rates. They have a mean of 76 and a standard deviation of 12.5. What are the minimum and maximum usual pulse rates? The minimum would be that mean minus 2 times standard deviation. Now I'm using mu and sigma because we're talking about the whole population of all people here and not a sample. So in this case, we have 76 minus 2 times 12.5. We get a minimum usual value of 51 beats per minute. Same thing for the maximum, except we're just adding 2 times the standard deviation. That gives us 101 beats per minute. Okay, the last part of the question here says, would a pulse rate of 110 be considered unusual? It would, because 110 is larger than the maximum usual value. Now, we've talked about bell curves a few times already. This is a really important part of this course because this shape occurs naturally and occurs with almost everything. If we were to measure the heights of adult males or the weights of giraffes, those distributions both take on the shape of a bell curve. We have some mean value, some mean weight of all giraffes, and then as we move away from that mean, it becomes less and less likely that we'll see a giraffe that's really heavy or really light. Now, the nice thing about bell curves is that the proportion of data within this curve stays consistent. Okay, so if we were to go 1 standard deviation, okay, in either direction, to the right, to the left, 68% of our data falls within that range. And this is a symmetric curve, which means that 68% is split in half, with 34% on the right of the mean and 34% on the left. If we move out 2 standard deviations to the right and to the left, 95% of the data in our distribution is within that range. Okay, again, it's symmetrical, where on the bottom here, all of these numbers add up to 95%, where we have half of it on the right, half of it on the left. Okay, and then the last number we have to remember, 99.7%, that's if we move out 3 standard deviations above and below the mean. So we can see pretty much everything in a bell-shaped curve, also known as a normal curve, lies within 3 standard deviations of the mean. There's pretty much nothing left outside of 3 standard deviations. Now, based on that, once we know that something is bell-shaped, we can answer a number of questions about it. Okay, for example, IQ scores have a bell-shaped distribution. They have a mean of 100 and a standard deviation of 15. So, following questions, what percentage of IQ scores are between 70 and 130? So here's our distribution here. Okay, I have it labeled along the bottom. The mean goes right in the middle. We had said the mean is 100. Okay, and then these numbers are just figured out by adding the standard deviation. So 1 standard deviation away, 2 standard deviations away, 3 standard deviations away. Okay, and then the same thing to the left, just subtracting. So to figure out what's between 70 and 130, okay, we can see these two numbers are right on the graph here. All right, those are marking the ends of that 95%. So 95% of people are going to have an IQ that's somewhere between 70 and 130. All right, part B, what percent of our IQ scores are less than 70? So now we're talking about this section over here. So this is outside of the 95%. Now, if we were talking about that left side and that right side, it's everything that's not here. So there's 5% to the outside of those two red lines there, okay, represented by the purple. All right, but we're only talking about half of it, only this side. Okay, and since it's a symmetrical curve, there's 2.5% on this side, and then another 2.5% on this side. Lastly, part C. So to be clear, our answer is 2.5%. Lastly, part C, what percentage are between 100 and 145? Okay, let's go green here. So 100. So we're here all the way up to here. Okay, so this is marking the end of that 99.7%. Okay, so if it was going from 55 to 145, we'd be talking about 99.7% of the data, but instead we're cutting that right in half. So it's going to be half of 99.7%. I think that's 49.85%. This is an equation that's not used as much. It's called Chebyshevs Theorem. It's fun to say. And it applies to distributions that are not bell-shaped. Okay, and this says that the proportion of any data lying within k standard deviations of the mean is always at least this value. Okay, 1 minus 1 over k squared. Okay, k has to be a positive number greater than 1. So with that said, let's say we have test scores with a mean of 85, standard deviation of 5. It's telling us that this is not bell-shaped, so we can't use the empirical rule. What fraction of the class scored within 3 standard deviations of the mean? So we're just doing that equation from the previous page, 1 minus 1 over 3 squared, which is 1 minus 1/9, 8/9. The last topic in this section is coefficient of variation. This gives us some idea of how large the standard deviation is in relation to the mean. It's a percentage, and we just take the standard deviation, we divide it by the mean, and we switch it to percents. Okay, that's for a sample value. Here we have the same notation just for a population. So let's say we're talking about the heights and weights of 40 males. We want to find the coefficient of variations for both of those values. So for heights, we are going to take the standard deviation and divide it by the mean and switch to a percentage. 3.02 divided by 68.34 gives us 4.42%. That's the coefficient of variation for the heights of these males. Same thing for the weights. 26.33 divided by the mean weight of 172.55, coefficient of variation of 15.26. We can see this is a lot larger than heights, which makes sense. Okay, we see a lot more variation in people's weights than we do people's heights.